This is Janet Hildreth doing my homework for reading pages 1 through 12 and 34 through 45. Learning point magnetic moments. It is the magnetic moment of hydrogen nuclei that align with the BO, not the hydrogen nuclei themselves. So what is a magnetic moment? Remember that it represents the direction of the north-south axis of a magnet and the amplitude of the magnetic field. Magnetic moments of hydrogen happen because there is one positively charged proton that spins. Remember, you need charge, your positive proton, and motion, the spin of that proton, to induce magnetism, which is stated by Faraday's law of electromagnetic induction. These magnetic moments also exhibit size and direction, better termed vector properties. They are represented by an arrow, and the interaction with the hydrogen's proton magnetic vector and the magnetic BO is what creates magnetic resonance. Back to the magnetic moments of hydrogen. They can align in one of two directions, parallel or anti-parallel to the BO. MRI focus on hydrogen because it is the most abundant atom in the body. So now we place these hydrogen atoms, which are essentially billions of tiny magnets within a larger magnetic field, or the BO, and they begin to interact with that strong magnetic field and move from random alignment to either parallel in the direction of the BO or anti-parallel in the direction opposite of the BO. How they arrange is based upon their energy level. Lower energy levels align with the direction of the BO or parallel, and higher energy levels align against the direction of the BO or anti-parallel. An example of this concept is a swimmer with a lot or high energy would be strong enough to swim against the current of the BO, but a weaker or lower energy swimmer would not swim against the current, yet go along with it. The energy of these nuclei is determined by the temperature of the patient. Nuclei that align parallel are referred to as spin up, and nuclei that are anti-parallel are referred to as spin down. This leads us to our next learning point. When the patient is introduced to the bore and the BO is introduced, there are parallel and anti-parallel alignments of the hydrogen nuclei. There are more lower energy or spin up nuclei than higher energy or spin down due to thermal equilibrium. So the excess of spin up nuclei cancel out the deficit of the spin down nuclei, producing a significant magnetic vector called the net magnetic vector for short. The difference of parallel and anti-parallel protons becomes smaller at lower magnetic field strengths, example BO of 1.5 Tesla, and larger at magnetic field strengths, example a BO of 3 Tesla. So here's an example. If you have 10 protons and 6 become parallel, then 4 would be anti-parallel. You would then have these cancel out with your net magnetic vector at 2. Now, if you introduced your stronger magnetic field, you would have some protons that are no longer strong enough to resist and go against that field. These would cancel out, and now you have a net magnetic vector of 8. Because of this, your signal is improved at higher Tesla. Moving on to the next learning point, we will be discussing the Larmor equation. Here we have the Larmor equation, and when protons are placed in a strong magnetic field, they start rotating around their axis at a frequency of loops per rotations per second, and this is determined by a constant number and the magnetic field strength. So here we have the W, which is what this refers to, the rotational speed or frequency of protons placed in the magnetic field, or your precessional frequency. Its unit is in megahertz. Your BO is your applied main static field, and that is measured in Tesla. And this is your proton-specific constant, known as your gyromagnetic ratio. Now for hydrogen, the gyromagnetic ratio is 42.57 megahertz per Tesla. What is important to remember is that all MR active nuclei have their own gyromagnetic constant. So if all MR active nuclei are introduced into the same field strength, they will precess at different frequencies, which is how hydrogen can be singled out and the other active nuclei can be ignored. The gyromagnetic ratio is constant, yet the BO is proportional to the Larmor frequency. So if you increase the Tesla of the BO, you will increase the precessional frequency or the rotational speed of hydrogen protons, thus increasing the Larmor frequency. The same would be true if you decrease the Tesla. The frequency would also decrease. So now we are moving on to Chapter 2's learning points, which is saturation. Let us recall that there are intrinsic contrast parameters that are inherent to the body's tissues and cannot be altered. They are the T1 recovery time, T2 decay time, proton density, flow and apparent diffusion coefficients. There are also extrinsic contrast parameters, which are selected by the MRI technologist. They are your repetition time, TR, echo time, TE, flip angles, time from inversion, your TI, turbo factor, echo train length, and B value. Knowing this, we understand that fat has a short T1, T2 time. This means for T1 contrast, the fat vector realigns with the BO faster than water. Fat has a high signal and appears bright on a T1 contrast image. And for T2, the transverse component of magnetization of fat decays faster. Because fat's magnitude of transverse magnetization is small, it appears dark on a T2 contrast image due to its low signal. Water has a long T1, T2 time. This means for T1 contrast, there's a smaller longitudinal component of magnetization of water. Water has a low signal and appears dark on a T1 contrast image. For T2, the magnitude of transverse magnetization of water is large. It has a high signal and appears bright on a T2 contrast image. So what does it mean by high signal and low signal? For there to be a high signal, there must be a large component of coherent magnetization in the transverse plane to induce a large signal in the coil. For there to be a low signal, there must be a small component of coherent magnetization in the transverse plane to induce a small signal in the coil. To demonstrate either T1, protein density, or T2 contrast, specific values are set for TR and TE for a given pulse sequence. So TR controls how far each vector recovers before the slice is excited by the next RF pulse. To obtain a T1 weighted image, your TR needs to be short so fat and water cannot fully return to the BO. TE controls the amount of T2 decay allowed before the signal is received. So the TE must be long enough to allow fat and water the time to decay to obtain a T2 weighted image. Proton density weighting, T1 and T2 contrast effects must be diminished so that PD can dominate. So you would need to have a long TR and a short TE to achieve proton density. So if the net magnetic vector is pushed beyond 90 degrees, i.e. the transverse plane, it is called partially saturated. And if pushed to a full 180 degrees, meaning back to the longitudinal plane, it is called fully saturated. T1 weighting occurs if partial saturation of fat and water occurs, so we are here. And if no saturation of fat and water occurs, then proton density weighting results. So before applying an RF pulse, fat and water are aligned with the BO. The first 90-degree RF pulse is applied, flipping water and fat to the transverse plane. Next, the RF pulse is removed, allowing fat and water to relax back towards the BO. Because fat has a shorter T1, it returns to the BO faster than water. Now, if the TR is short and the next RF pulse is applied, fat and water vectors will be pushed past the transverse plane because they did not fully relax back to the BO. Because fat has a greater longitudinal magnetization available to be flipped into the transverse plane, it has a higher signal and appears bright where water appears dark, and a T1 weighted image results. So, if the TR is longer and the T1 times of the tissues than fat and water have the time to fully recover before following the RF pulse, then they are flipped just to the transverse plane, resulting in no saturation. The areas bright to dark have then to rely on their individual proton densities rather than the rate of recovery of their longitudinal components. Tissues with a high proton density are bright, where tissues with a low proton density are dark. So moving on, we need to understand T2 star decay. Remember that regular T2 decay is dependent on the properties of fat and water themselves because it is resultant of the magnetic fields of the nuclei interacting with each other. T2 star decay also involves inhomogeneities, which are areas within the magnetic field that do not exactly match the external magnetic field strength. So if the nuclei lie in the area of inhomogeneity with a larger field strength, its precessional frequency increases and vice versa. The relative acceleration and deceleration as results of these inhomogeneities, as well as the differences in the precessional frequency of certain tissues, causes dephasing of the spins and produces free induction decay, or a loss of signal due to relaxation. So now we move on to our next learning point, discussing 180-degree rephasing. This point uses the use of toy cars to explain what essentially happens during 180-degree rephasing. You have 3 different levels of car on a racetrack. The pulse is applied starting the race. All the cars head out at different speeds, becoming out of phase or incoherent with each other. More dephasing occurs the longer the race has run. Now, a 180-degree RF pulse is applied and the cars about face, so that the fastest car is now last and the slowest car is now first in terms of returning back to their original start. When all the cars return back to the start at the same time, they become back in phase or coherent. And if they were magnetic moments rather than toy cars, a spin echo would be generated at the time they became coherent. The length of time from the start to returning back to the start line corresponds to your echo time. So now we move on to our last learning point, which is understanding weighting. One basic rule for analyzing your images is to look at the water content. If water content has a high signal, it's most likely a T2 weighted image acquiring with a long TE. If water content has a low signal, it is most likely a T1 weighted image acquired with a short TR. Fat is an unreliable marker because it can be bright on many different types of weighting depending on the pulse sequence applied. Thank you very much for tuning in to Janet Hildreth and MRI.